Hi everyone, my name is Sarah Wiegreffe, and today I'm going to be presenting our work on measuring association between labels and free text rationales. This is joint work with my co-authors Anna Marasović and Noah Smith. In this work, our goal is to understand the model's decision-making processes for individual instances. This has use cases including debugging, validating safety, and revealing unintended biases and behavior. Crucially, this requires explanations that accurately reflect model internals, sometimes referred to as faithful explanation. We'll now briefly describe the two predominant forms of explanation in NLP. Here's an example from the Common Sense QA dataset. The question is, while eating a hamburger with friends, what are people trying to do? The answer choices are have fun, tasty, or indigestion, and the correct answer choice is have fun. The COSI dataset is a dataset of human annotated explanations that has been collected on top of Common Sense QA. Here, a human annotator has written the following highlight or extractive explanation, which is a subset of the input tokens. They've highlighted the phrase hamburger with friends to explain the label have fun. The second type of explanation provided is a free text or abstractive explanation. Here, the human annotator has written, usually a hamburger with friends indicates a good time. As we can see in this example, the free text explanation fills in the reasoning step to adequately explain the answer that the highlight explanation does not. We'll come back to this later. In prior work, we introduced pipeline models as an architecture for faithful highlight explanation. The pipeline model consists of two steps. In the first step, we have a support and extractor model. The support model is trained to perform a prediction task. Here, labeling the sentiment of a movie review. The extractor model extracts a highlight explanation from the input to the support model. In the second step, a predictor model is trained to consume only the highlighted explanation, and then to predict the sentiment. Crucially, these are two independently trained models with no gradient flow between them. This architecture is based on the sufficiency assumption, which states that the explanation should be sufficient to make the prediction on its own. In fact, that's the only reason that pipeline models can achieve comparable accuracy to end-to-end models. As large pre-trained language models have reached state-of-the-art performance on machine reading and information extraction style tasks, the NLP community has shifted to creating tasks where information is not stated explicitly in the input by design. We've already seen an example of Common Sense QA. Here's another example from the EMNLP, or Stanford Natural Language Inference dataset. It also has an associated dataset of human annotated explanations, both highlights and free text. This dataset is called ESNLI. We argue that free text explanations are going to become increasingly important as the community shifts to these style of tasks, specifically because these tasks will require explanations that can explicitly state implicit information and that aren't limited to what is explicitly stated in the input tokens. Which brings me to the overarching research question that we pose in our work. We ask, can models faithfully explain instance-level predictions in natural language? We don't posit to answer this question completely, but rather to begin to propose empirical methods for investigating it, and to motivate its importance as a subfield of study. Here are the two primary research questions of our work. We split our investigation into two parts. In the first part, we test the faithfulness of free text rationales in a model architecture specifically designed for faithful highlights, the pipeline. We ask, can we apply pipelines to tasks requiring free text explanation? In the second half, we test a general architecture that is designed for task performance and not for providing faithful rationalization, which we call a joint multitask model. In the same way that prior work has situated models for highlight explanations on a faithfulness gradient, we aim to explore where free text explanations and their associated models can fit on this spectrum. We present a case study on the T5 architecture. In our first experiment, we revisit the sufficiency assumption. In pipelines for free text explanations, the support and extractor models are replaced by an explanation generator. This means that the first step, the input to rationale step, is not explicitly trained on label signal. However, intuitively, we hypothesize that free text explanations are often written to accompany an input and don't make sense fully without it. To test whether the sufficiency assumption also holds for free text rationales, we simply reappend the input to the rationale in the predictor model and retrain the architecture. We then test how much performance improves by including the input alongside the rationale. Here we can see the plot of performance of each dataset when only the explanation is included as input. When we reappend the input as well, we see that all tasks improve slightly and the gain is more substantial for the COSI datasets. This allows us to conclude that sufficiency is not a universally valid assumption for free text rationales. In our second experiment in this section, we ask, do pipelines produce cascading errors? Prior work has highlighted that there is an implicit label prediction step happening inside the explanation generator, because in order to explain a prediction, one must decide what one is predicting first. This leads to task obfuscation, because the input to rationale model is not trained on label signal. In this set of experiments, we ask, can the input to rationale model infer the label well when it's not trained on label signal? To do this, we train and test various versions of our predictor model, feeding different explanations as the input. First, we compare the performance of the pipeline model generated explanations to the gold explanations when fed into the predictor model. We see that they perform significantly worse. We then compare this to explanations trained on label signal and explanation generation tasks jointly. Here we can see that all tasks have a small improvement, but again, the improvement is substantial for the COSI dataset. This leads us to conclude that training on label signal improves task prediction on rationales, and it's important to generate good quality explanations and avoid cascading errors. Taken together, the two experiments of our first research question have led us to conclude that pipelines are not easily extensible to free text explanation settings. This leads us to ask about another type of architecture, the joint multitask model. Joint or self-explaining models are simply models trained on a multitask objective, both to emulate gold labels and to emulate gold explanations written by human users. They're a popular class of models for a number of reasons. They have high task performance. Generally, adding an explanation generation task does not hurt label prediction. They're more parameter efficient than pipelines, and they're flexible and easy to use. Here's an example using our running common sense QA example. For the input, when eating a hamburger with friends, what are people trying to do? Our joint T5 model decodes both a predicted label, have fun, and a predicted explanation. Crucially, this model is trained on 2 task losses. It's also massively over-parameterized, which leads us to ask how much parameter sharing is actually occurring between the tasks. In order to judge how faithful the explanations coming from a joint model are, we need to understand how tied the mechanisms predicting labels and producing generated explanations are within the joint model. We actually don't observe that they are always tied in practice. For example, for the instance, a crane uses many a steel cable when working a what, and the answer choices ship, winch, and construction site. The model correctly predicts the correct answer, construction site. However, it explains a totally different answer choice, producing the explanation cranes are used to work on ships. Our first experiment in this section tests something we call robustness equivalence. Our axiom is that the label prediction and explanation generation mechanisms should be equally robust or non-robust to noise. Our method involves injecting zero-mean Gaussian noise into the first layer embeddings of the T5 joint model. We use the variance term to control the amount of noise that we apply. Here are the results on a single instance, our running example. We can see that from a sigma squared value of 0 to 15, both the predicted label and the predicted explanation are stable. The predicted label doesn't change, and the predicted explanation changes, but stays valid for the given instance. From a sigma squared value of 20 to 35, we observe that both mechanisms are unstable. Scaling these up using automated metrics to investigate entire datasets, we can observe whether robustness equivalence holds across the datasets. Here are the results for ESNLI. On the left, we have a graph showing the percent of stable labels and the accuracy of the model at the task at different levels of sigma squared. Here we observe that the inflection point happens around a value of 25. Similarly, on our automated metric of rationale quality, simulatability, we observe that the function minimum also occurs at a value of 25. In our second set of experiments on joint models, we propose a feature we call feature importance agreement. Our axiom here is that important input tokens for label prediction and explanation generation should be similar. To do this, we use gradient attribution. We simply decompose our gradient attribution scores into 2 components, those with respect to logits of the predicted label and those with respect to logits of the predicted explanation. This results in 2 ranked lists of the input tokens, one indicating the importance of the input tokens to the label prediction, and one indicating the importance of the tokens to the explanation. We use an occlusion-based method called ROR to investigate the relationship between these token importances. To do this, we delete tokens important for one task and measure how performance drops on the other. Here on the left, we can observe task accuracy as we delete tokens important to the predicted explanation. This is the green line. We can see that it is far below the blue line, which indicates random token deletions, indicating that tokens that are deemed important for the explanation are also important for the label prediction task. We repeat the same experiment, deleting tokens important for label prediction and judging how they affect our automated metric of rationale quality, simulatability. All datasets indicate similar trends. We conclude that the joint T5 model does illustrate feature importance agreement on the datasets studied, at least in one direction. Revisiting our research questions from the beginning, we first asked whether we could apply pipeline architectures to tasks requiring free text explanations. In our second question, we then asked how faithful are joint multitask models and attempted to begin situating them on the faithfulness spectrum proposed by Jacobi and Goldberg. Our takeaways are as follows. Free text explanation is critical for reasoning and understanding style tasks in NLP. This is the primary argument of our paper. We then investigated pipeline models and found they are not well suited to tasks requiring free text explanation. We demonstrated that joint T5 models on 3 datasets pass necessary sanity checks that we propose, although we highlight that these are necessary and not sufficient conditions for faithfulness, but they do reveal interesting insights about model behavior. Our ultimate goal of this work is a better understanding of large language models as explanation generators. In order to answer our broad research question, can models faithfully explain instance-level predictions in natural language? We hope our paper motivates further studies on the faithfulness and reliability of large language models as free text explanation generators.